The three best predictors of how well you'll age, Julia Jilhava. If you want to learn a fish's age, simply take one of its scales and count the number of bands radiating from its center. For trees, you can count their rings. For narwhals, their tusk layers. And for blue whales, their layers of earwax. When it comes to humans, scientists have yet to find any visible traits that mark our age with anywhere near the same specificity. But in the past few decades, they've discovered small, invisible markers hidden within the body that do change over time. And they may hold even more information about our health history and future. The first of these markers was discovered in the 1990s. Telomeres are repetitive sequences at the ends of DNA strands that protect chromosomes from fusing together. However, each time a cell divides, part of the telomere is cut off. These small losses can add up over time, and once telomeres get too short, cells lose their ability to replicate and eventually die. This gradual shrinking process led scientists to identify telomere length as a promising, albeit imperfect, marker of aging. As technology has advanced, scientists learn how to detect even more discrete changes, like the addition of individual molecular tags called methyl groups. This DNA methylation can control gene expression, including switching genes on and off. It can occur rapidly and frequently, allowing cells to respond to different situations and perform normal functions. Yet researchers notice that at certain sites in the genome, methylation levels tend to change more gradually and predictably as we age. The reason for this is still unknown, but these changes may be associated with stress or caused by random errors during DNA replication. By measuring DNA methylation patterns from hundreds or thousands of these sites, scientists have developed what they call epigenetic clocks as another way to measure aging. A third way our bodies change over time is through inflammation. Proteins that are important components of the immune system generally increase when we get sick, then decrease again once our body has recovered. But as we get older, their baseline levels rise, resulting in chronic low-level inflammation. This process is called inflammaging. Scientists are still unsure why it occurs, but it could be due to repeated encounters with pathogens and other stressors. Another explanation could be the process of cellular senescence. When cells get old and stop dividing, they secrete inflammatory proteins. And by measuring the level of these proteins, scientists have developed yet another clock that can accurately measure aging. While all three of these markers are great additions to the age estimation toolbox, instead, they are best at estimating something called biological age. Biological age is a measure of how well your body is functioning, how much damage your cells and organs have accumulated, and your overall risk for certain health problems. Unlike chronological clocks, biological clocks tick at different rates for different people due to genetic differences, as well as health, stress, and many other environmental factors. And different tissues and organs within the body may even biologically age at different speeds. In many ways, these clocks are still a work in progress. For example, most experts recommend against personalized biological age testing. While these tests are commercially available, the value and accuracy of these measurements remain unclear. Currently, these tools work best at the population level, when data from many individuals are analyzed. However, many scientists hope to change this in the future, as accurately tracking this information could revolutionize personalized healthcare. For example, one day a person's accelerated biological age might help doctors detect an unknown health condition much earlier. And other researchers are searching for ways to slow down or even turn back these biological clocks. Though so far, most attempts at this have been largely unsuccessful. Besides, researchers still don't know if telomeres, inflammation, or epigenetics are actually to blame for aging, or they are simply neutral markers of other processes happening in the body. We may be learning to read the language of aging, but we still have a way to go in understanding its grammar.